Hey everyone, we're going to kick off our fun-filled year of calculus with section 3.1a, which is about the mean value theorem. So in calculus, there's three different existence theorems. You've actually already learned about the first one, the intermediate value theorem. We're also going to learn about the mean value theorem and the extreme value theorem. So in this video, we're specifically going to focus on the MVT, the mean value theorem. I want to just point out that this video is spliced from an old one, so if it seems a little choppy in some places, now you know. Well, enjoy!
Hey everyone, in this video today we are going to be looking at the mean value theorem. Before we get to the mean value theorem though, we're going to look at a theorem called Rolle's theorem. So Rolle's theorem says if y equals f of x is continuous on the closed interval ab, differentiable on the open interval ab, and f of a is equal to f of b, then there exists a number c in the interval ab such that f prime of c is equal to 0. Okay, I want you to take a second. I want you to pause the video. I want you to try to imagine what this is telling us. So think about a graph. Think about what all of these things are telling us. We'll talk about it in just a moment. All right, hopefully you've taken some time and looked at it. So this is what I've come up with. So first, we know that the function needs to be continuous and it needs to be differentiable, meaning that there can't be any sharp terms, any discontinuities, etc. We also know that between two values a and b, their outputs or their y values are going to be the same. So it looks something like this. So what Rolle's theorem is telling us is that within this interval ab, there's going to be some number c that exists where the slope at that point c, or the derivative of that point, is 0. So here I see that we have a horizontal tangent. So that's all Rolle's theorem is saying. If our y values are the same, then there has to be this point where we have a horizontal tangent and our slope is 0. Alright, Rolle's theorem is going to be used to kind of help us explain mean value theorem. And we have a mean value theorem for derivatives. Eventually we'll have another mean value theorem. So mean value theorem says if y equals f of x is continuous at every point of the closed interval ab and is differentiable at every point of its interior ab, so the open interval, then there's at least one point c where the average rate of change equals the instantaneous rate of change. So mathematically, this is written as f prime of c is equal to f of b minus f of a all over b minus a. Okay, a lot of things. First of all, mean value theorem has some important pieces that we need to keep in mind. First thing is, if the mean value theorem is going to apply, we need to make sure that it's continuous on the closed interval. And we need to make sure that it is differentiable on the open interval. And really, we could combine both of these together, and we could say that it is differentiable on the closed interval AB. Because remember, differentiability implies continuity, so we can just combine it together. Alright, so let's take a little closer look at what this is mathematically saying. So looking at this first part, f prime of c, well, we know, okay, that's the derivative of f evaluated at the point c. So this is our instantaneous slope at x equals c. And, okay, looking over here, f of b minus f of a all over b minus a, well, that's just going to be the average slope of the secant line between the values of a and b. So we're just saying that the instantaneous slope at this point is equal to the average slope of a secant line that's connecting points A and B. So let's take a look over, I'm going to switch over to Desmos. Let's take a look at what this is saying. So here, okay, I have this function, and notice here this green line that I have is our secant line. So remember, a secant line is just any line that's connecting 2 points. Alright, okay, so now I'm going to introduce a tangent line, and its tangent at this point is C. So I'm going to move C around, and I can do that. Here we go. And so what the mean value theorem is saying is that there is going to be a point, I'm going to zoom in a little bit, a point C, that's too far, there we go, where the slope of the secant line is equal to the point, or is the same, equal to the slope of the tangent line at that point C. So this is my point C, and I see that my slopes are equal, so I have parallel lines. And really, going back over here, Rolle's theorem is really saying the same thing. It's just a specific case of the mean value theorem. I see that if I were to connect my points A and B, hey look, I have two horizontal lines. They both have a slope of 0. So this is the mean value theorem again. All right, so I'm going to show you a proof of the mean value theorem in class. We're going to use Rolle's theorem to help prove it. I'm not going to do that in the video though. I want to jump straight into some application. So, switching over a page, looking at example 1, we're going to state whether or not the function satisfies the hypothesis of the mean value theorem. And if it does, we're going to find the value of C in the interval AB that satisfies the equation, so our mean value theorem equation. So the hypothesis of the mean value theorem is that it needs to be continuous on the closed interval and differentiable on the open interval. So looking at A, we have the function y equals the absolute value of x on our interval -1 to 1. All right, and I think down below it says, provide graphical support for your answers. So looking at A, let's just sketch a little graph of this. Okay, well this is just our parent function of the absolute value function. Okay, we're going from -1 to 1. Okay, well I know that's just going to look something like this. And we're making sure it continues. All right, so looking at my graph, okay, it is continuous on the closed interval AB, but I do see that we have a sharp turn at x equals 0. So because we have a sharp turn, that means that our derivative is going to be undefined. It doesn't exist. So the mean value theorem doesn't apply. So okay, let's write some of this down. How do we want to say this? So it's continuous on our closed interval, but not differentiable at x equals 0. So therefore, if you haven't seen this before, our 3 dots here, it really means just therefore. It's a shorthanded math. Therefore, our mean value theorem doesn't apply. And I might just say that this is a sharp turn, just so we remember. All right. Okay, well, let's look at B. A was a bust. Let's look at B. So B, we have our function y equals natural log of 3x plus 5, and we're looking at that on the interval -4/3 to 2/3. All right, okay, so a little bit about this function. And let's get our little graph here. Nice. Okay, I know that the natural log function isn't going to be defined for the entire set of real numbers. We are going to have a limited domain, but I do know that it's going to be undefined where the argument of this is going to be, it's going to be defined for where it's greater than 0. So I know that I'm going to have a vertical asymptote wherever 3x plus 5 is greater than 0, or is equal to 0, I guess. So that means that our domain is greater than -5/3. So we do have a vertical asymptote here. And then I think our function is just going to look something like this. But, okay, looking at the interval that we've been given, we have -4/3 to 2/3. So we are only looking from, let's say, about here to here. So just this part of our function. And I do see that it is continuous on that interval, and it's also going to be differentiable on that interval. So therefore, we are going to satisfy the mean value theorem. So let's see. So it is continuous and differentiable on the interval we've been given. Oops, that's close. There we go. And so therefore, mean value theorem is satisfied. That is close enough. Okay, so what that means now is we are going to focus now on finding this C. So I want to know where on this interval is there a point C. Let's see. My marker needs to be skinny. Okay, so if I were to connect these 2 points, here's my secant line. I'm trying to figure out where on this interval I'm going to have a tangent line that has the same slope. So we need to calculate our average slope and we need to calculate our instantaneous slope. So let's come down below. Okay, so our average slope is just going to be our f of b minus f of a all over b minus a. So it's going to be the natural log of 3 times 2/3 plus 5 minus natural log of 3 times negative 4/3 plus 5 over, let's see, that's going to be 2/3 minus negative 4/3. So really we're going to be adding here. All right, let's see. So inside our argument, okay, 3 times 2/3, well, that's just going to be 2, 2 plus 5. So we're going to have natural log of 7. And here, 3 times negative 4/3, it's going to be negative 4. Negative 4 plus 5, that's going to be 1. So minus natural log of 1 over, and then we have 2/3 plus 4/3. That's going to be 6/3. So that's equal to 2. And then I think we can simplify this farther. I know that a natural log of 1 is just 0, so our average slope is natural log 7 over 2. And I'm going to plug this into my calculator. Let's just kind of evaluate what this decimal is. And I'm just going to write it out for a couple of places just because let's have a really good approximation. So this is approximately 0.972955. So just plug it in your calculator. That's our decimal approximation. All right, okay, so now we need our instantaneous slope. Okay, so our instantaneous slope is going to come from our derivative. So let's take the derivative of natural log of 3x plus 5. So y prime, okay, this is going to be it's going to be a chain rule. So derivative of the outside, that's 1 over 3x plus 5. Derivative of the inside, that's 3. So that's 3 over 3x plus 5. So we are evaluating where y prime, our derivative, we're evaluating it at x equals c, which, lucky for us, that's 3 over 3c plus 5. Okay, so let's see what we have. So right now we know what our instantaneous slope is. We've evaluated at C, and we know what our average slope is. We actually have a value for that. We're trying to figure out this value of C where these two are equal. So I'm going to set them equal to each other. That's 3 over 3c plus 5 equals the natural log of 7 over 2. So where the instantaneous slope is equal to the average slope. All right, and then we could use our decimal approximation here. We're just trying to get pretty close. 3c plus 5 equals 0.972955. And I believe that we can solve this. Go algebra. And when we do that, we should get that c is equal to negative 0.639. All right, okay, so if you have a question about how to do this algebra, come and see me, but otherwise, here's our value of c. And remember, in calculus, we're always going to take it out to the nearest, the nearest thousand, so 3 decimal places. All right, okay, so we just did this. Let's see what this actually looks like on our graph. So I'm going to come over, shows back to Desmos, and let's see, okay, I have our function, natural log of 3x plus 5. I have our secant line, and I have it for both of our interval values. So this was 2/3, this was negative 4/3, and so here's our secant line. And so we found a value of c that was negative 0.0639, where our slopes were the same. And hey, look over here, this was our slope at its decimal, 0.9714, well, pretty close to it, because we, approximated our values here. So here, I can see that my lines are parallel. That's exactly what we were finding. So this value of C made this happen. Thanks, calculus.
All right, that's all for now in this video. I will see y'all later in class, and we will pick up where we left off.